Okay, in this lecture, we're going to talk about taking the curl of the electric field. And the learning objective is basically just to have a good conceptual understanding of what is meant by the curl of a vector field in general. Okay, so the question is, what does it mean to take the curl? And generally, it's a little bit harder, I think, to understand what curl is. I mean, in some ways it's easier, but in some ways I think it's harder to look at a field and tell what the curl might be without actually calculating it. In general, though, the curl, it's a measure of the circulation of a vector field. The circulation of a vector field. Okay. In a force field, okay, if I think about it as a force field, okay, it would measure the amount of push around a closed path. Okay, so just to review this, it's a measure of the circulation of a vector field. In a force field, it would measure the amount of, oops, I forgot a word, the amount of push around a closed path. Okay, so the question looks a little bit like this, okay? So if I draw a vector field here in purple, okay, I want you, this one is a uniform field, okay, so uniform, we're going to call it a flow, and it's okay to think of it, again, if we're just trying to think conceptually, thinking of it by like a flow of air or maybe a flow of water. And we're going to put a little paddle wheel in this flow, okay? And the paddle wheel is going to help us figure out whether the curl is 0 or non-zero. And again, just like divergence, we're really measuring the curl at a particular point in our vector field, okay? Eventually, we'll talk about summing the curl everywhere. But when we're just thinking about taking the curl, we're looking at a value at a specific point. Okay, so I'm going to put this paddle in at a specific point, and I'm going to ask, will it spin? Okay, will it spin? In this case, let me just label this. This is like a paddle wheel. Okay, in this case, no. Okay, no, it won't spin. And the reason why is because you've got as much force kind of pushing on this paddle that would make it go in the counterclockwise direction as you have force pushing right on this side of this paddle, which would cause it to go in the clockwise direction. So those two forces, or better torques, would cancel out, and you would end up getting no net torque on this particular paddle wheel. Okay, so in this case, we've got equal and opposite. We're going to call it forces because it doesn't necessarily have to be a force field on different parts of the paddle. But that's how we want to think about it when we're just looking at a picture. Okay, let's draw another type of vector field. In this case, I'm going to draw a field where the strength of the field actually gets stronger down the page here. Okay, so the way I've drawn these vectors, we're going to assume that the flow is stronger down the page. Okay, and the same thing, I'm going to draw a little paddle wheel in here. And the question is, if I draw a paddle wheel, whether or not that paddle wheel would turn at a particular location in my field here. Okay, so will it spin? You guys can, if you want, think about that for a second. Okay, but I would argue that yes, okay, in this case it will spin. And if I think about that, it's because down here on this side of my paddle wheel, I've got a stronger vector. I can think of that as like a stronger force field pushing on this side than I have counter pushing on the other side. Okay, so this particular paddle wheel is going to end up turning counterclockwise. So it's going to spin counterclockwise as viewed from above. And that's because, again, around a closed path, I could think about the closed path being just the edge of these paddles. Okay, the amount of push is not equal and opposite. There is a net push or a net torque. Okay. Okay, so we're going to keep thinking about it in terms of a force. So what I'm going to do here is I'm going to draw a closed path. Okay, so closed path, and we're going to call this DL. Okay, so it's like taking a line integral, okay, around a closed path. Okay, and along this path, I'm going to draw some force vectors, okay? So we're just thinking of it like a force now. It doesn't necessarily have to be a force field, okay? But all these purple vectors are going to be force vectors. These are the vectors that you would measure in this particular field along this blue line. Let's see here. Okay, so it looks something like that. Okay, and if I'm still thinking of this like a force field, then we want to figure out the total push along the loop. Okay, so the total push along our closed path could be calculated with the following integral. Okay, so it'd be the total push force would be equal to the line integral of our force dotted with dl. Okay, and so what is dl? Well, dl is going to be, right, the little tangent vector that I could draw along our path. Okay, so as I'm actually doing this sum at each point along our path, I can, right, do a sum of that particular force and that particular element of the path. And doing the sum, I'm actually going to do an integral. Okay, so in this way, okay, I'm going to argue that curl can be thought of as, okay, the total push force divided by the area. Okay, so I can use this particular integral to calculate the total push force, but then I want to divide it by the area. Okay, but this is just kind of analogous to divergence. Okay, I want to know the curl at a particular point. Okay, so I want to know or be able to calculate the curl at a particular point. So to do that, I'm going to, of course, take a limit as the area goes to 0 of this idea of taking the total push force divided by the area. Okay, and when I do that, that's what ends up being equal to the del operator crossed with our force field. Okay, so I want you to think about, we're going to shrink this area, this total area here, okay, all the way down to the middle point, and we're going to be able to define the curl at a particular location by taking the area down to 0. Okay, no, all of this is for, okay, this is a reminder, all of this we've talking about force fields, but in general, this idea to find the circulation of any vector field. Okay, it doesn't even have to be something that means anything, right? If you have a two-dimensional or three-dimensional field of vectors, you can still calculate the curl, but it's nice to have an example of something that we can think about physically. And force, obviously, we're pretty familiar with that. One more note before I end this one that makes it different from the divergence is that when you take the curl of a vector field, you get a vector. The curl is a vector. You guys remember the divergence was a scalar, so they're different in that way. Action of the curl vector, it always points perpendicular to the plane of circulation. In the direction of the right-hand rule. So that should help you figure out which direction the curl should point. If I was looking at this particular example here, the curl or the circulation would be counterclockwise. So if I wrap my fingers around, my thumb would point out of the page. So in this case, the curl is out of the page.